for today, I want to show you guys something cool. This is a really, it's not real difficult stuff, but it's extremely useful in calculus. It's called L'Hopital's rule. Anybody speak French? A little bit? You know what that means in French? Yeah, but it's the hospital, but it's actually a person's name. Yeah. Guillaume L'Hopital was a good French mathematician. What's that? I don't know. That's, yeah. Parents had a sense of humor, I guess. I don't know. So, what this is for, remember, we got to go back to limits for a second. This is a long time ago, we built up an understanding of limits because in order to define the derivative function, that depends on limits, right? Depends on the limit of the difference quotient as h goes to 0, and you'll remember that stuff, I'm sure. You haven't done it in a while, but when we were talking limits, we said something really important. When we're evaluating a limit, one of three things could happen. The first two are simple. The third one required more investigation. Either we get an answer, right? We get a numerical answer without a 0 on the bottom, right? We get something of the form. In fact, let's go back and just review this very briefly. We get some answer where the denominator is not equal to 0, okay? And we're done, right? We evaluated the limit directly. It was a simple one. We got an answer, end of story. The second thing that could have happened, you remember what that was? What was the second thing that could have happened where we were also done? Yeah, okay, right. If we got a 0 on the bottom, if we got something like a divided by 0, where a is not equal to 0, then we were also done, right? That was no big deal. I mean, we ended up taking a one-sided limit there, but we ended up getting an answer that was either going to be positive infinity or negative infinity, right? When we took one-sided limits. Now, the third thing was the thing that always required us to, that's what the assignments were mostly on, right? Was this type where the limit of f of x as x approached a equaled what? 0 over 0, yeah. And that's what we called an indeterminate form. And we always said that equaled more work, right? And we had to do a bunch of stuff. We had techniques for simplifying these limits. I'm going to add one more to the mix here. I can't remember if we ever did any like this. But another one that's also indeterminate that works the same way would be when we evaluate our limit directly, we got infinity over infinity, works exactly the same way. We would just have to do more work until we resolved that limit, right? Until we moved this type 3 limit up into one of the top two categories, right? And what that really corresponded to was we just traded the function that we were evaluating the limit for. We traded that for a function that filled in a hole, right? 0 over 0 meant that there was a hole in the function there. And we filled that in, and one of these things happened, okay? Well, this could be a load of work, and that's what, you guys spent a lot of time solving problems like that. Don't throw stuff at me, but there is an easier way to do this. And the reason I didn't show you this earlier is because it's like a catch-22. L'Hopital's rule is a really simple way of evaluating limits that are indeterminate forms, but it requires you to know how to differentiate. And we needed the limit to know how to differentiate. So you see why we had to do this the long way initially, because we hadn't yet used the limits to come up with the the process of differentiating. Now we're pros at that. And so we're able to do this much more easily. So here's L'Hopital's rule. Suppose that functions f and g are differentiable. Now let's kind of break this down a little bit. Are differentiable on an open interval I containing the number c, except possibly at c. Okay, so what does that mean? The functions are differentiable. Differentiable just means take the derivativable, right? These are functions that we can differentiate. Now, it's possible that the derivatives don't exist at c. That's possible, okay? And we'll see some examples where that's true, but we have to be able to differentiate these functions, okay? If we can differentiate these functions on this open interval, then if we end up, when we try to evaluate f of x over g of x, I'm going to try to directly evaluate this limit, which means I'm just going to plug in values, right? I'm going to plug c into both of those. If I do that, and when I try to directly evaluate the limit, I get indeterminate forms that look like 0 divided by 0 or infinity divided by infinity. Here's the trick. We could just differentiate the top and the bottom separately, not using the quotient rule, but we're just going to differentiate the top, that's going to be f prime of x, and differentiate the bottom, that's g prime of x. And if I evaluate that limit and I get an answer that is no longer indeterminate, then it turns out that the limit of the ratio of the derivatives is equal to the limit of the ratio of the functions. Crazy, okay? Now, this, you have to be careful with this though, and I'm going to say this again and again, because L'Hopital's rule is only guaranteed to work if the original function that we're trying to evaluate is indeterminate. If it's not indeterminate to begin with, L'Hopital's rule, the derivative, may not give you a limit that's in agreement with the original limit. Okay? You can only apply it if you're starting off with an indeterminate form. Okay, I think the best thing to do is, because there's a lot of theory that I've just thrown at you, is to like put this into practice and go through an example or two, and you'll see how easy this is. Okay? So, steps for finding a limit using L'Hopital's rule. The first thing is to verify that f over g, we only apply this if we've got a ratio, right? If we've got a function where I have f on top and g on the bottom. Otherwise, L'Hopital's rule doesn't make sense. There are some ways, heads up, there are some other indeterminate forms, like for example, 0 times infinity is also indeterminate, but we're not going to look at that one today. We'll come back after we've had a little understanding of how to deal with these 0 divided by 0 or infinity divided by infinity. Then we can tackle some other indeterminate forms. We'll have some strategies that we can employ, okay? So we check that it's indeterminate. Step 2, we're going to differentiate the top and the bottom separately. Again, no quotient rule. We evaluate the derivatives or differentiate top and bottom separately. And then we find the limit of f prime divided by g prime. And if that is not indeterminate, that's our answer. Now, what happens if we take the derivatives of the top and the bottom and it's still indeterminate? What do you think we do? We just do it again. Yeah. We just differentiate again the top and the bottom until we get an answer. Is it possible we could have a function that cycles and never gives us an answer? Yes, it is possible, right? And then that would be one where we don't know the value of the limit. Okay, that's presumably one where the limit doesn't exist. Okay. So in words, if the limit of f of x over g of x leads to 0 over 0 or infinity over infinity, L'Hopital's rule states that the limit of the quotient equals the limit of the quotient of their derivatives. Okay? So here's an example. Like, what about the limit of tangent x over 6x as x approaches 0. Well, if I try to directly evaluate that limit, I get 0 on the top and the bottom, right? Okay, this is, we don't have a lot of people taking the AP exam, but on the AP exam, it would be important if this was in a section where you were doing an open-ended question, it's very important that you verify that the original function is indeterminate before you apply L'Hopital's rule, or you're not doing it correctly if you don't verify that. So we differentiate. Well, the derivative of tangent x is secant squared x. Derivative of 6x is 6. And so we get, now we've got secant squared x on the top and 6 on the bottom. And if I evaluate that limit as x approaches 0, I get 6 on the bottom. Well, what's the limit of secant squared x as x approaches 0? I always think of secant in terms of, secant and cosecant in terms of sine and cosine. Secant is what? Reciprocal of cosine, right? So the cosine of 0 is what? 1, right? So then the secant of 0 is also 1. So secant squared of 0 is 1 squared, or 1. So I end up with 1/6, and that's my answer. Okay? Now, it's kind of interesting. I haven't thought about this in the past, but this would be kind of cool to look at this graphically, maybe. How about if we do that? Ooh, this could be pretty cool. Yeah, I like this idea. This might give you a little insight. So if we try this with Desmos graphing, let's call f of x, let's just call that the function tangent x over 6x. And we want to look at the limit as x approaches 0. Okay, well, if I try to evaluate this at 0, what's it going to tell me? Undefined, yeah. But if I zoom in real closely, well, it is approaching a value, right? Even though the function doesn't exist at that one spot, it's certainly approaching from the left and the right a specific value, okay? Let's graph the ratio of the derivatives. Let's call that g of x. We said that was secant squared divided by 6. Okay, notice if I zoom in now, secant squared, even though it's a completely different function, the green and red functions are completely different. What's important here? Yeah, that they approach the same point as x approaches 0, right? I mean, they are completely different looking functions, right? But all we care about is the fact that the green function now does have, it is defined, and their limits are the same. Okay? Well, that's kind of a cool way to show it. I like that. I remember that. Okay? Try another one. Oops. How about this guy? Let's try this one. So what's our first step? Yeah, we got to see if it's indeterminate. Well, if I try to evaluate this at 0, sine of 0 is 0. So I get 0 minus 0 over 0. So it is indeterminate, right? Okay. So what are we going to do then? Okay, differentiate the top and the bottom. So this would equal the limit as x approaches 0 of what on the top? Cosine x minus 1 on the bottom? 2x. Okay, let's try that one. What's the derivative of cosine 0? 1. Okay, so I get on the top, I get 0. On the bottom, I get 0. What do? Do it again. Right. Okay, so then this is equal to the derivative of the top, which is what? Over. Okay, now that I can evaluate. What's that give me? 0 over 2, which is 0. Done. Okay. Oh, why do I have all these filled in? Okay, let's try that one. Okay, we got to verify first of all, right? Okay, what's the limit of the top? As x approaches infinity? Infinity. Okay, bottom, e to the infinity is obviously infinity, right? Okay, indeterminate. Infinity over infinity, right? So we got to differentiate. Any predictions what's going to happen here? What's going to happen? Anybody? Zero's right. Anybody see why that might be the case? You know, I did something's goofy here. I've got, hang on one sec. I think we were talking simplifying limits of indeterminate forms yesterday. So we left off, remember we were saying, this is the one we left off on, right? And this is just a pretty straightforward L'Hopital's rule problem. So we verified that this is one that looks like an infinity over infinity, right? If we evaluate this directly, as x approaches 0 from the right, we said that cotangent of x would approach positive infinity, and log x would approach negative infinity. And the reason was because of the shape of this log graph, right? And you guys might be a little rusty on that, but you want to get familiar. Like when you think log x, just in your mind, you're thinking that graph, and that helps a ton, right? So on this graph, we can see the domain of a log function is just only positive values of x. And as we approach 0, we can never get to 0, but as we approach 0 from the right, the output value, the value of the function approaches negative infinity, right? So this is classic L'Hopital's rule. We're just going to differentiate the top and differentiate the bottom until it's no longer indeterminate. Okay, well, after one step, it is indeterminate, right? Because what is the value of cosecant x as x approaches 0 plus? Cosecant's 1 over sine, right? Think what a sine function looks like. Let's go back to the unit circle for a second, right? If we think unit circle as x approaches 0 from positive values, isn't that just going to be a really small angle right there? Small positive angle. Well, what's the sine of a very small angle going to be? It's going to approach 0, isn't it, right? Positive 0. And so I'm going to end up getting, 0 squared times negative 1. I'm just going to get a 0 on top, aren't I? Right? On the bottom, obviously 1 over x as x approaches 0 plus is also going to give me, that's going to give me what on the bottom then I'm going to get? Oh, why did I say 0? That's going to be, cosecant is 1 over that, so that's going to be infinite, isn't it? Right? You get my point? Sine is going to be approaching 0, so cosecant is going to be the reciprocal of sine. So I'm going to get 1 over a really small value. So it's going to be infinite. I'm going to get infinite on the top and infinite on the bottom. And we don't care about the signs. We just know we have some infinity on the top, some infinity on the bottom. That's indeterminate. So we got to go again. Okay, but we don't want to be hasty about this. We want to be smart about taking this limit. Is there something we could do to the argument of the limit? In other words, what we're taking the limit of to make that process easier. Right now, it's not like we could do this, but taking the derivative of cosecant squared, that's going to be a chain rule problem. that's going to involve derivatives of cosecants times cosecants. Agreed? That doesn't sound great, does it? Right? Okay. 1 over x, that's x to the minus 1. That's going to be a chain rule problem. Or a quotient rule, if you really want to use quotient rule, right? What could I do to make that better? What's in the orange bubble? Because the limit doesn't care what's in the orange bubble as long as they're algebraically equivalent. I can rewrite that ratio in a more convenient way. Like 1 divided by 1 over x just equals what? X, right? Yeah. 1 over x is just x. Okay, cosecant of x, you already told me, is 1 over sine, right? So couldn't I rewrite this, everything in the bubble? I could just write it as I've got my negative, but the x is going to go to the top, and I'm just going to get a sine squared x on the bottom, right? Isn't that better? I think that's better. Okay, so now we could apply L'Hopital's rule again, because that's indeterminate. Okay, so what does that equal then? The derivative of the top is what? -1. That's a good sign, isn't it? What's the derivative of sine squared x? Sine squared x. What's that going to be? Everybody agree? 2 sine x cosine x? Give me thumbs on that. You guys, thumbs up if you agree, thumbs down if you disagree. Right. Well, what's the outermost layer in that derivative? Squared, right? Derivative of hand squared is 2 hand, right? So the first step is going to be 2 sine x. What's the next layer? Sine. Okay, so derivative of sine is cosine. Okay, good. So that's going to give me a 2 sine x cosine x. Okay, let's see what that gives me now. If I evaluate this at 0 plus, what's that going to give me? I'm going to get -1 on the top. What am I going to get on the bottom? I'm going to get 0, aren't I? Oh, whoops. Thank you. Yeah. Okay. Right. What's that going to give me? So I'm going to get, on the bottom, I'm going to get 2 times, what's the sine of 0 plus? This is good review because we're doing limits, infinite limits here. What's the sine of 0 plus? 0 plus, right? Everybody agree? That's 0 plus. Sine of a really small angle is going to give me a really small positive value in quadrant 1. Okay, so we'll just call that 0 plus. And what's the cosine of 0 plus? 1. So on the bottom, 2 times 0 plus times 1 is just 0 plus, isn't it? 2 0 plus is 0 plus. So I end up with -1 over 0 plus, which is what? Yeah, a 0 on the bottom gives me an infinity, right? 1 on top, 0 on the bottom gives me infinity. So this part, I gotta be real careful here. Oops, the color coding is critical here on this one. So that part right there gives me an infinity, and this part, negative divided by positive, gives me negative, right? Done. Okay. So we had to do 2 iterations of L'Hopital's rule, but we got our answer. Okay? All right, so next